Before we dive into rendering the model from last time in one of the next episodes in Redshift, I want to show you some finishing touches, because the model is not perfect yet. This is how far we went in the last episode. This is the file from the last episode. It's just that I cleaned it up a little bit and reorganized it to make it look nicer, but the structure is exactly the same. If you have a close look, you see that these valleys here, or these lines where the spheres intersect, are very sharp. Especially if I get rid of the wireframe display, you see this is really near to a shading artifact. So it would be nice to smooth this out, and that is possible. If you remember, we created a SDF volume, and we derived these onion skins from this volume, and this volume is very sharp too, because it's just a union of different spherical volumes. So if you append a volume blur here, you can smooth this out. If you append it and make it visible, everything vanishes because the radius is too big. Let's make it smaller, say 0.03, and you see now everything is nice and smooth. Don't bother with this artifact here. That is because of the bounding box of the volume ending here. Because we are only interested in the lower part of these onion skins, that is not a problem. So now connect the volume blur here and make the loop run. And you see, now we have nice, smooth transitions. A lot nicer than before. Great. The next thing is that we created onion skins with fixed distances between each other. So the distance from one skin to the next is always the same, because we increment the ISO value by a fixed amount. It would be nice to add a little variation to this, especially having a curve to remap these values and to be able to art direct the distances between the individual onion skins would be nice, I think. So let's add this. Remember that we used this wrangle here to remap the I value to the ISO value. So let's move this down a little bit and maybe rename the point wrangle to something a little more descriptive, like calculate isoval, like so. And let's press Alt-E over this expression field to open the code editor, and let's look at the code. So what did we do? We brought in two values, the number of iterations and the ival last time, and then we fitted the ival between 0 and the number of iterations to a new range of 0 to 0.3 to generate these onion skins. So the minimum ISO value is 0 after this operation, and the maximum ISO value is 0.3. Now I would like to introduce a channel ramp. A channel ramp creates an interface element, a curve, that can be used to remap a value interactively using this interface curve. But it takes in a range of 0 to 1, and after this fit operation, our range is between 0 and 0.3. So we have to restructure our code a little bit to make it work. The first thing is we are reading in the I value. So the first thing we have to do is to make sure that the I value is in the range between 0 and 1, such that we can pass it on to the channel ramp. So create a fit operation around this channel function here that brings in the I value. We will use this expression here, this statement, channel I value, as the value to remap. So after that comes a comma. And then we want to remap it from 0, which is a minimum input, to num iterations, num iter, and the output range should be 0 to 1. Don't forget the closing bracket. So with this new fit statement, we now have a I value that ranges from 0 to 1. Great, because now what we can do is we can override I value with a channel ramp function. chramp. Channel ramp will evaluate one of these ramp interface elements, and you see in a second how this looks. Let's first write the line. So channel ramp, let's call it, and that is a parameter name, iso distrib maybe, like so. the parameter name, and then comes the value that we want to pass on to this curve, and that is ival. And don't get confused here, because I am writing to ival and I'm reading from ival. But that is totally okay in coding. It's first reading the old value of ival that I set here, and then it's writing to ival, overriding whatever was in this variable. I could create a new variable, but then I just have another variable and more RAM, which is not a problem here, but it's just easier to do it this way and to just reuse this variable here. So now I have this ival here fed through a channel ramp, but we don't have this interface element here. Press apply and accept. And if you now press this button again, it creates this channel ramp interface element. Because channel ramp is a function very similar to channel. It just reads values from an interface element. And as soon as you press this button, the interface element is created if it is not already there. And here isodistrib is the name of the interface element. So great, now I have a ramp, and I can use this ramp to interactively remap my value. But the code is not entirely correct yet, because we have this second fit operation that is fitting iValue to isoval. And this still uses the code from before. It's fitting between 0 and numiter to 0 and 0.3. And that is not valid anymore, because now the range of ival after this channel ramp is no longer 0 to numiter, but now it's 0 to 1. So let's replace numiter by 1. Press apply, wait for the loop to calculate, and you have the same result as before. Let's press accept, because this was all we had to change to the code to implement this channel ramp. But what you can do now is, by clicking on this little arrow, you can expand the element to be bigger, such that you can work easier with it. And now by clicking here on the curve, you can introduce new points, like so. And if you move them around, we can now change the mapping of our values. And by introducing a second point maybe, I can make this steeper, like so. And now you see I influenced the distances between the individual onion skins, because now the onion skins are not equally distributed throughout the range between 0 and 1, or later between 0 and 0.3, but we have this mapping here, and this mapping gives larger gaps in the middle region and smaller gaps at the end of the curve. And that looks a lot more interesting if you ask me. If you want to alter this further, maybe make this node visible, because then the loop does not have to cook every single time. Let's make it like this maybe, then make the loop visible again. And you see now we have here a lot of onion skins at the beginning and a lot of onion skins at the end, and in the middle a large gap, which makes it far more interesting. So now maybe move this back a little bit to make the contrast not as harsh, and maybe go to the repeat end and up the number of iterations to just generate more onion skins, like so, and this looks quite interesting. So now let's care about colorizing our model. It would be great to have a parametric color on our model, such that each individual onion skin has its own color. And we can do this if we derive the color from an attribute. And remember, we are using a different ISO value for each onion skin. And each individual ISO value is created from the ival that we read in here on this node. So if we write this ival to an attribute, we can use it later to create a color. But be careful, we have to do it after the convert volume. Because here, before the convert volume, we are dealing with volumes, and volumes cannot have primitive or point attributes because there are no primitives or points. After the convert volume, we have standard Houdini geometry, and we can write attributes to this geometry. So let's create another wrangle, another point wrangle, and append it here after the convert volume. And let's call it set ival. Because what I want to do is I want to set the ival to the point as an attribute. So hover over the expression and press Alt-E to open the code editor. And let's put in a very easy expression here. We want to do exactly the same thing as before. First, we want to read from a parameter field. And in this parameter field, we will put the same detail expression as before to read the I value. So the very first line will read integer ival is channel, and this time it's channel integer because we want to read an integer, and the field should be called ival again, like so, and we terminate the line with a semicolon. So this time I'm reading in an integer value called ival, and because it's an integer, I tell the channel function that it should read an integer by using the channel chi function here. And then, as soon as I have this value, I'm writing add ival. That is a shortcut syntax for creating an attribute and writing to it is ival. Don't confuse these two. That here, with the add in front, is the attribute called ival, and that here, without the add, is referring to this variable here. That is all the code we need. Press apply and accept. And now press this button to create this ival interface element. What we can do is we can copy the HScript expression from here. Just select everything with string A, copy it, and paste it here, like so. Now we read the I value from the detail attribute from the repeat begin 1 metadata 1 and set it to an attribute. So if you make this one here visible and go to the geometry spreadsheet, now we have an ival of 15. That is great. Now that this is working on one onion skin, we can just connect it here to the merge and afterwards clean up the merge by deleting the convert volume, like so. And if everything went right after the loop, we should have an ival for all the points of the individual onion skins. So all the individual onion skins, or all points belonging to one onion skin, now have the same ival. And we can use this with a color node to create color. So append a color node here after the loop. Make it visible and switch the color type from constant to ramp from attribute, because that is what we want to create. And it is asking for the attribute name that we want to use to remap the color, and this is ival. That is the name of the attribute we just created. And if we do that, everything turns white, because the range here is not correct. Our range is going from 0 to 15, because the I value is counting the iterations. So go from 0 to 15 here, and you see now it's working. The very first onion skin is very dark, and the last one is light. And now you can use this ramp here to create the color you like. If you want to set a color, you can press this color button here, and you are presented with this color chooser dialog. A quicker way is to just press on this color wheel, then it will switch to RGB mode. If you want to use RGB, you can do this. And if you want to use HSV, you can press again and it will switch to HSV. That is my preferred method of choosing colors. And you can set the hue, the saturation, and the value now. And like this, you can create a color ramp for your model that can be used later on in the shading context to drive a shader. The next thing is that I want to cut my model. At the moment it is terminating here where the bounding box of the volume ends, and I would like to cut a plane right through the volume or through the model, because I think it will look nicer if we cut it open. A very quick way to cut with a plane is the clip stop. So put down a clip stop and connect it here. Wait a second for the clip sub to do its thing, and you see, as soon as I make it visible, it clips my model and throws one half of the model away. And you see it's already looking far more interesting like this. But I would love to keep the lower part and get rid of the upper part. So go to this keep menu here and state that it should keep primitives below the plane, like so. And maybe we want to move the plane to a different location. So why not putting 0.2 here, like so. That looks quite nice. Cool. This can be rendered. Here all these nice intricate structures are visible now that we cutted the volume. But what is missing is that we don't have faces here between the individual onion skins. It would be nice if at least between some of these onion skins caps would exist. So how could we model these caps? Well, one way to do it is by using a Boolean operation. We could create a box and then just Boolean this model here with a box. And this way we would create these caps, basically. And a procedural way to create this box is, again, the bounds sub. So lay down a bound sub and connect it here after the clip, and you see you get a box that is including the entire model. If I would do a Boolean operation now, not much would happen because this bounding box is outside of the entire model. But we can change this by using the lower and upper padding parameters. So if we make the box a little larger to make sure that it does not intersect the model in all directions, we have a box that is slightly larger than the model, but the upper padding in Y is the only value that we want to decrease to minus 0.1. That way, if we template this clip for a second, you see that we now have a box that is outside of the model everywhere, but in Y. And now we can use a Boolean, put down a Boolean, and connect the bounds to the first input and the clip to the second input. Make the Boolean visible. And at the moment, it's trying to intersect both. And both inputs are set to solid geometry. But that's not the case. We have as input B the clip, and that is surface geometry. So first set B to surface, and then set the operation to shader. And what it now does, get rid of this template, what it now does is it shaders the input A with the geometry in input B. So it cuts the box in stripes, so to speak, and thus creates exactly these caps that we are after. At the moment we have caps everywhere, but we can go in manually and delete everything that we don't need. So with the Boolean selected, click here on this area to expand the toolbar and go to select. And now you get this toolbar here at the top that lets you specify what you want to select. In our case, primitives, that is already selected. And if you now hover here over the primitive, they get highlighted, and you can just click them, and they will indicate that they are selected because they turn yellow. So select first the box, primitives, everything, the bottom with shift. And now carefully select some, but not all of these stripes. Just keep some in a way that looks interesting. That one, for example, I delete like so. Let's delete this one and this in the middle here, like so. It's totally up to you which one you delete and which you keep. The only target is to make it look interesting. And now we want to blast these. I can create a blast node here in the network editor, but then my selection will be lost. Instead, press Tab while hovering over the viewport and select Blast from the menu. If you create the node here, it gets appended here in the network editor, but at the same time here in the group field, all the primitives are put in that I selected. So that is the way that you are working with selections in Houdini. You create the selections in the viewport, and then you create the node that has to use the selection, for example a blast or a group, over the viewport. And then it will transfer the selection directly into this group field here. Very handy. So great. So now we have these caps. But we not only have the caps, but we have the caps and all the other geometry. That is in principle a very good thing because we need both, but we want to be able to alter the cap geometry independently because the caps don't have a color yet. We have to give them a color. So let's somehow split this apart. How can we split it? Well, if we go back to the Boolean, there is this section here that is called output primitive groups. And these groups are created automatically during the Boolean process. Let's tick on B inside A. All the primitives of B that are inside of A will go to this group. And that is exactly the geometry that we have here after the Boolean. So, after the blast, now we have all these polygons here that are not the cap geometry in this group. If you middle click on the blast, you see that I now have a prim group B inside A. So now I can append another blast here after the selection and just go to this little menu here and select B inside A, and it will blast away everything but the cap geometry. But because I need the other geometry too, I can now by Alt dragging duplicate this blast and just invert its operation by checking delete non-selected, and this will give me the geometry that I just blasted from the first geometry stream. So this is the original geometry, and in this stream here we now have the caps. Time to fix the color. We have two problems here. First, the caps do not have a color, and second, if you look closely to this geometry here, get rid of the wireframe maybe, you see that at the very edge they have a white color now. And that is because the bounds geometry that we used for the Boolean was white, and it transferred this color attribute to the resulting model. So we have to somehow transfer the original color back to this geometry. And fortunately we have a sub that can do that, and that is called the attribute transfer sub. So create an attribute transfer and connect this geometry here to the very first input. This node will transfer attributes from the second geometry connected to the second port to the geometry connected to the first port. And it will do so by proximity. So it will look up the positions in 3D and it will transfer the color that it finds nearby. So connect this second port here to the original model, to the color node, like so, and make it visible. And you see, now it transfers the color from this model here by proximity to our new model. And all the white artifacts here at the edge are gone. So here the blast shows artifacts or white stripes, and with the attribute transfer these are gone. Now this is beautiful. Okay, now let's color the caps. The problem with coloring the caps, if I quickly make this geometry visible again, is that both edges of the caps have different colors. So the caps somehow have to interpolate the color. And that is not very easy with geometry like this. We have just n-gons here that will be triangulated later or during rendering, but it is not enough geometry to really interpolate colors, because colors can only interpolate it over points, and there are very few points in this geometry. So to generate a geometry that is better suited for color interpolation, let's remesh these. There is a SOP that does the remeshing, so find it by typing remesh and append it here, make it visible, and it will remesh our geometry. At the moment it is set very coarsely, so we have large triangles here. And the resolution is determined by this target edge length parameter. This says that the edge length should be 0.2 for the remeshed edges. If we go lower with this value, we can create a lot more geometry. And you can easily tell, if you look at the wireframe, that this geometry is far better suited to do color interpolation. So let's do this remesh operation like so. And now we have a geometry that is better suited for interpolation. But how do we put the correct color on this mesh? Well, we do exactly the same thing as on the other side. By alt dragging, we can copy this attribute transfer, but this time we connect the geometry from the remesh to this attribute transfer. And the attribute transfer does its thing. It transfers the color attributes here on the sides. And because it has enough geometry, the colors will beautifully mix, as you can see here. So now we get beautiful gradients. But because of the proximity nature of this attribute transfer, it just looks up nearby points. We have here a little banding here and there. And to get rid of this banding, we can just blur the color. So the last step is to create an attribute blur node, because we want to blur an attribute, and this attribute is called CD, like so. And let's up the blurring iterations to say 50. And if we do that, you see that now all this banding is gone. Here you have it, and after the blur, everything looks perfect. And now we can just merge these two geometry streams again to create our final model. The last thing that is missing is to fix the normals by just appending a normal node at the very end, like so. And here you have the finished model that we can now render. We have interesting gaps, we have caps, not everywhere. So we just introduced a lot of variation to this model to make it far more interesting than before. The very last step before we go into rendering in one of the next episodes is that I would love to have some spheres present here in these holes. Not everywhere, but here and there. And remember that we started out with a lot of spheres here with this copy to points. That were the spheres that we used to create the volume that we used to derive this model from. So I would love to use some of these spheres in the final render. But we converted these spheres to a volume and they're gone, so we have to somehow bring them into another object to use them there. And that can be easily done in Houdini. To make it easier for us to bring them to another object, let's create a null. And let's append this null here. This null contains the spheres. And let's call this out caps spheres. It's a good practice to call this capital out at the beginning, just because later on, if we are asked to select this node, this will be at the top of the list because of the capitals. So now we have this out point here, and we can go back with our display flag to the normal, and now we go one level up. At the moment in our scene, we just have one geometry, the volumetric onion skins. Time to generate a second geometry. So lay down a geonode. Call it spheres and dive inside. Inside you find the file sub. As always, get rid of it. Instead, we want to bring in the spheres from the other object. That can be done with an object merge node. The object merge node is used to read geometry from another object and bring it into this object. Go here to the object field and press this little button. This will give you this chooser. Here you see the entire scene. Go into volumetric onion skins, and in there you find all the nodes of the setup. And now you understand why I called this out with capital letters, because then I find it easily because it is here at the top of the list. That is a node I created where the spheres come out. So press accept, and here you have the spheres. But for my final render, I don't want to use all the spheres, so let's manually go in, select some and delete them. Again, go to the selection mode, but this time it's hard to select entire spheres because if we are going to primitive mode, we just select individual faces. What can we do? Well, there is this selection menu. And if you go into this menu, you can say 3D connected geometry. If you do that, instead of selecting individual primitives, it always selects entire groups of primitives that are connected in 3D. And that makes it easy to select entire spheres. So now just select the spheres you want to get rid of, like so. And again, over the viewport, press Tab and blast, and the spheres are gone. Remember, Houdini is not dealing with objects here, it's dealing with geometry. This menu here just helps to select all the primitives that are connected in 3D, and that is the case here with the spheres. Maybe repeat the operation to get rid of this and this sphere. Blast, like so. That is nice. So I want to keep these 4 spheres just to make the result visually more interesting. And that, if you go up one level, is really the geometry that I want to render in the render episode. So thanks a lot for listening. I hope you learned something. I hope you enjoyed finishing this model and caring about all the little details. And I'm very much looking forward to rendering this in Redshift.